Hi, it's budget scope meter review time again, and on the workbench today is a MUSTOOL MDS9208. It has a 6000 counts multimeter, a 12 MHz 50 meg samples per second oscilloscope, and a 100 kHz function generator built in. And you can get it for just around $60. Banggood sent in this unit for me to do a review. As usual, I will leave a product link in the video description below for those who are interested in getting one after watching this video. Now, like the ZT702S I reviewed a while ago, this meter obviously is geared towards the budget market as well. Here I have the ZT702S on the side, and you can see the MDS9208 is even smaller. And here is a standard-sized multimeter for comparison. You get an idea of the size of this meter. Now, one of the key differences between this meter and the ZT702S is that it has a standard multimeter style diode rotary switch, and it operates just like your standard multimeter. Also, you notice that there's no BNC input on this multimeter, as the MDS9208 uses the multimeter probes as the oscilloscope signal input. For low frequencies, this shouldn't be an issue. Now, to be clear, it is not ideal for measuring frequencies in the megahertz range, as there is no way for you to compensate the probe's frequency response. But the scope only goes up to 12 MHz anyway. And also keep in mind, when using this kind of low-end oscilloscopes, especially this kind of low-end handheld ones, you are most likely just using it to confirm whether a signal is present or not, and get some sense of the basic characteristics of the signal. You are most likely not going to do any precision measurements. Here is the box the MDS9208 came in. Besides the meter itself, you also get a soft carrying pouch, a USB cable for charging, and of course, a user manual. The leads themselves are pretty much just what you'd expect for a cheap multimeter, but not much to complain here either. Alright, let's turn it on. And as you expected from this kind of multimeter switch, you get into the multimeter mode by default. And I like that actually, as for me, this would not be my everyday oscilloscope, and I would probably only be using the oscilloscope function occasionally to confirm the presence of a signal, and most of the time I would just use it as a multimeter. As you just saw, the boot up time was actually pretty quick. Let's switch to a few different ranges and take a look here. And one thing interesting is that it seems different ranges are illuminated by different colors via these LEDs on the side and on the diode itself. Now, I think the philosophy here might be that you could quickly identify the range you are in without having to look at the labels, but I'm not sure if the manufacturer had given much thought into which color corresponds to which range. As first of all, there are too many colors, and the colors don't really mean much. If I were designing it, I probably would make the color red for all these current ranges here, so that at least you know you should be paying attention. Anyway, some people may like it. Let me know what you think in the comment section below. A better approach, in my opinion, short of using a split socket design through which you can test the presence of probes in the specific socket, is what Kaiwitz did in their meters, which would illuminate the corresponding sockets briefly, so at least you have some visual indication on whether you have plugged in your leads in the right place or not. Let me actually show you that, in case you haven't seen the review videos yet. So here's a Kaiwitz meter. You can see if I turn it on, it will tell you that here are where your leads should go. And let's turn a different range. Let's go to the current range. You will see that the corresponding sockets are lit up. So this is actually not a bad design. And of course, these LEDs also draw at least a couple milliamps current. But this meter is actually pretty energy efficient. It has a single 1500 milliamp hour 18650 cell, and the spec says the current draw in this multimeter mode is roughly 80 milliamps, and it goes up to 300 milliamps in oscilloscope mode. So the runtime is really not a concern. Of course, we will need to verify that later in the teardown if I can. Also, when you first power on the meter, you will see the status of the meter displayed very briefly on the LCD screen here. By default, the meter will power off automatically after 15 minutes of inactivity. And by default, these buttons make very loud beeps when pressed. You can disable the auto power off by holding the F1 key while turning on the meter, and let me just show you here. And you can see you get a confirmation from the status display. To turn off the sound, all you need to do is press and hold the F4 key while turning on the meter. Again, you can see the display status reflecting that. Now let's test out the DC range with my EDC voltage standard, and we'll do it 1 volt at a time. By the way, you can see that the stand of this multimeter and oscilloscope is very sturdy. It has this ridge and it does not flex at all. Alright, let me dial up the volts. 1, 2, 3, 4, 5, 6, and because this is a 6,000 count meter, I would expect if I go to 7, yep, it will lose 1 digit. 7, 8, 9, 10. And you can see it's pretty much bang on, no issues at all. By the way, you can do manual ranging if you desire by pressing the F4 key under the range indicator here. You can see here we can range to 600 volts, no problem. And you can switch to the secondary functions by using the F3 key. You can see the select. So that's the secondary function. So in this case, it's for AC, for DC, and for frequency measurement, so on and so forth. I have to say that the UI design is very intuitive. Now let's take a look at the AC measurement. For that, I'm using my Unity UT61E Plus as a reference here. So it doesn't seem that the update rate of the MDS9208 is as fast as the Unity, of course, but you can see we are updating about 2 or 3 times per second. The only thing is when it's changing different ranges, it's not showing the measured voltage here. And it appears the threshold for that high voltage indicator, or the beeps you heard, comes on at around 24 volts. The accuracy of the MDS9208 is fairly decent. In AC mode, it's specified as 1.5% plus 10 digits. So as you can see, the readings from these 2 meters are agreeing with each other, and they're definitely within specification. So let me dial up the variac all the way up. It appears that there's another beep at some point here. One feature that is really cool on this MDS9208 is its implementation of the min-max functionality. Let me demonstrate it here. To enable the min-max measurement, you actually press this PH, that's peak and hold. I think the label could have been a little bit more intuitive, but that's essentially what it is for. So if I press that, you will see that we have this run and stop. What that is actually defines an interval, and within that interval, it captures the minimum and maximum voltage. So let me zoom in a little bit. You can see we have a min, max on the display here. So let me just quickly change my variac. You can see that the max is captured at 145.3, and the low depends on where I last dialed in, and the number right now is at 73.1. So now if I wanted to reset this, I just press stop. So now if I change the voltage, you can see that the min-max no longer changes. And of course, if I want to reset and do it again, I just press reset, and I can start doing the min-max again. So you can see this feature is definitely very useful. Now we also have a hold function, and that is actually more traditional. For that, let's actually exit this. All you do is you simply press the save button, and it will actually hold the display value with this big display here. So for example, if I now adjust the voltage, you will see that this main display no longer changes. That's the value held at 83.5, but we do have this smaller display that shows you the current voltage reading. So that's really a nice touch. The MDS9208 also has some data logging capability as well. All you need to do is press and hold the save button. First, let me get out of the hold mode here. And let me press and hold, save. And you will see that we do have this database where you can store the value. And it's really easy to use. If you press save, the current value will be saved in the database. Let's say we change the voltage down a little bit. And let's see if we can save another value. No, it actually saved the previous value. I wonder if we need to get out of this mode first. And let's go back. So now let's try to save again. Yeah, so it seems that while you're in this mode, it already captured whatever the value you had before. To be honest, I'm not sure if this feature is that useful, as you have to record each of the values manually, and there's no way for you to automatically trigger to record a value at a fixed interval. We even have a dedicated millivolt range on this meter, and in this range you get 1 extra digit resolution. So in theory, you can measure down to 10 microvolts. So let's give that a go. And right now we're outputting exactly 1 millivolt from the MV216A voltage standard. And you can see that we do have some discrepancy here. We have roughly 30 microvolts out, but that shouldn't be an issue as that is still within the spec. So what we're trying to test here is whether or not we can use this meter to discern the last significant digit change, which is in the 10 microvolts range. So let's increase the voltage output by 10 microvolts. And you can see we actually are able to register that. So let me increase by another 10 microvolts. Yep, no issues at all. So definitely this meter has a 10 microvolts resolution in this millivolt range. Now let's take a look at the ohm range. Let's short out the leads first. And you can see that the range switching is on the slower side, but that's somewhat to be expected. And let's just route it out. So now we're actually fixed at this 600 ohm range. So let's measure a 100 ohm precision resistor. And we shouldn't have any range switching here, so that should be pretty fast. And the result is fairly accurate here. And just for a good measure, let's measure another resistor here. So let me remove the rail and set it to auto here. And this resistor here, let's see. Yeah, it did take a few seconds for it to stabilize. Now, this is a 4.7 kilo ohm resistor. We're measuring it with no problem here. According to the manual, you can measure up to 60 mega ohms with this meter. And next, let's test the diode mode. And for that, I'm going to measure a white LED. A lot of the meters I tested before were having some issues measuring the forward voltage drop of a white LED. So let's see if we can do that here with this meter. And you can see we have no problem. The forward voltage drop of this white LED is 2.66 volts. Very good. Now let's move on to the continuity mode. Now, the leads themselves are not gold-plated, so sometimes they don't make good contact, but once the contact is made, you can see it doesn't have any issue, and the result is definitely latched. So that's very good. What is a little bit unusual for this meter is it has a separate capacitance measurement range. The first capacitor we're going to measure is this 22 picofarads capacitor, and let's give it a go. What is weird is when I move the leads, you can see that we're not getting any changes in the capacitance measured. So let's see. I think the measurement is actually on the lower side, but nevertheless, it is able to register at least in the ballpark of that capacitor. And now let me go straight to this 15 millifarads capacitor here. So let's give it a go. And I expect it to be very slow. Actually, it's probably faster than some of the other meters I have tested, but you can see the reading is definitely in the ballpark, no issues at all. According to the spec, the highest frequency the MDS9208 can measure is 20 MHz. And you can see right now we're outputting a 20 MHz square wave signal from the UTG962E, and we're measuring that with no problem. And right now the amplitude is at 2 volts peak to peak. Now I cannot go any higher than 20 MHz because that's the limit of the function generator. So later on we'll take a look at a sinusoidal to see if we can push the envelope a little bit higher. But right now what I want to show you is the secondary display here. That's the duty cycle. As you can see right now we're measuring just a little bit off of that 50%. So let me actually reduce the frequency here to see if we get that perfect 50%. So right now we're at 10 megahertz. You can see we're measuring 50.68. And let's actually change that duty cycle. So I'm going to change it to 60. Yeah, it's a little bit off. Okay, so let me further reduce the frequency, and let's just reduce it to, let's do 1 kilohertz. So I just reduced the frequency to 1 kilohertz, and now you can see the 50% is bang on. Now let me change that duty cycle to something else. And let's see if we get an accurate reading. So let's change to 60. Yep, 70, 80, 90, and let's go back to 10%. No problem. So it seems that the duty cycle measurement definitely is heavily dependent on the frequency, and obviously you are only going to get reliable reading at lower frequencies. And right now I changed the waveform type to a sinusoidal, and you can see at 2 volts peak to peak we are able to measure up to 20 megahertz. In fact, if I just increase the frequency a little bit, I don't think you are able to measure. Well, 21 is still okay, but 22 you can't measure anything anymore. So that spec frequency range is definitely correct. Now if I increase the amplitude a little bit, for example, let's just do all the way up to 10 volts, and you're actually able to push the frequency much higher. So now let's go to 30 megahertz, 40, 50, no. So at least you can go to 41, 2, 3, yeah, 42 megahertz. So that is quite good. Next, let's do some current measurements. And this time I'm only going to use this 100 microamp current standard to do the measurement. I'm only going to test one range, as the other ranges are probably going to be similar. And let's give it a go. You can see no issues at all. While I was playing around, I actually noticed something interesting. If I just left the leads in the voltage measurement sockets, I actually get some interesting readings. For example, right now, if I try to measure the 100 microamps, you see that we got a 10.1 microamp reading. That is actually very interesting, because right now we're in the current range. You shouldn't get any readings. And if I go to the milliamp, you see we actually get a 1 milliamp reading. And if you go to 10 amps, we're getting a 0.2 amps reading. Now, this is actually not the voltage either. For example, right now in the microamp range, we're reading 10.1. You would think, okay, that's probably coincides with the battery voltage of the current source. But actually, that's not the case. So if I go to the volt mode here, and you can see the output voltage is at around 17 volts. So I'm not entirely sure what exactly is going on here, but clearly this meter does not have the proper range isolation between the current measurement and the other measurements. So just something to pay attention to. Obviously, you should always double check your lead's position before doing measurements. And finally, let's get to the oscilloscope mode. I know you guys are probably dying to see that. So to do that, all you do is, as long as you're in the volt or millivolts range, you can actually switch to oscilloscope by pressing down the Alt key. Press and hold it. So now we're in the oscilloscope mode. Now I'm outputting a 1 MHz 10 volts peak to peak signal from my UTG962E. So let me enable the output. And let's see if we can acquire that signal. So let's do auto. Yep, we acquired the signal with no problem. And you can probably see from the annunciator at the bottom here, that is indeed a 1 MHz signal here. Now the measured peak to peak is a little bit off, but hey, it's a $60 scope. And let me increase the output frequency and see how high we can go. 2 MHz, 3, 4, 5, 6. And you can see the update rate is not that great. Let me reacquire the signal here. Actually, let's use the menu to figure out how to do that. So let's go to time, and I can probably increase. Yeah, okay, that's quite intuitive. And so now we're at the lowest time base. So let's keep increasing the frequency. Right now we're at 6 megahertz. 7, 8, 9, 10, no problem. 11, 12. Okay, the display becomes a little bit unstable at 12 megahertz, but you can see we are able to capture that 12 megahertz right there. And the amplitude seems to be fine. Now you have to take this with a grain of salt because we don't have a proper terminated cable here. Nevertheless, you are able to see the full 12 megahertz bandwidth on this oscilloscope with no problem. So let me keep increasing to 13. No, 13, probably 12 is the highest because the frequency here, I'm changing to 13 right now, and you can see it's still 12. So the hardware is not able to measure anything above 12 megahertz. So let's just leave it there. And in fact, if I just keep increasing the frequency, you'll see some aliasing start happening here. So now it's 14, 15, and amplitude gets higher, and you can see the frequency actually started going all over the place. And let's do 20 megahertz. You can see that the waveform actually looks as if it was from a lower frequency signal, but that's actually due to the aliasing here. So anyway, it appears the maximum frequency we can measure is just at 12 megahertz. Alright, I just turned off the beeping sound as it's getting to be a little bit annoying. So let's take a closer look at some of the menu items here. And from here, as we saw earlier, you can adjust the time base and come back. We can also adjust the attenuation here. No problem. And you can see that when the signal is clipped, we do not have a signal out of the range indicator here. And that's typical for most of the scopes. But this could be a problem, especially if you don't know what the signal is supposed to look like. Anyway, so let's come back here. And that's the amplitude. Next is adjusting the trigger level. And you can see here, we actually have quite a few options here. You can adjust the trigger level, and if you can see that little triangle on the right-hand side, that's the trigger level. So if I just adjust it up, you can see that it's moving up. And I can move it back down again. So we can reset it to the middle, and also we can change the trigger mode. So right now you can see this is single shot, this is normal, and this is the automatic trigger we're using right now. And of course, we can trigger on the rising edge or on the falling edge. So although you only have 4 keys to play with, you can actually adjust the settings of the scope relatively easily because they designed it very intuitively here. Now let's add a 1 kHz amplitude modulation to the signal here. And I'm going to change the time here. Let's see if we can get to a stable signal here. Yep. And you can see we can actually capture the signal with no problem at all. As you can see, the update rate is actually not that fast. It's roughly about 3 times per second. Let me actually change it to a frequency modulated signal and see if we are able to observe the rapid waveform changes. And here is a frequency modulated signal. It is on top of the same 1 MHz carrier, and except right now we're doing a 100 Hz modulation, and with a frequency deviation of 1 MHz. And unfortunately, because of the refresh rate is so low, you are not able to see any changes. So once in a while, you do get this kind of glitch, and you can see that the waveform frequency is changing, but most of the time, you are not able to catch up with that change. So that's a limitation of this scope for sure. Although this is a very cheap multimeter, it still offers you the single shot capability here. Now, the single shot mode is a little bit glitchy, and in fact I have to try multiple times to just get it triggered, but nevertheless you do have the capability to take a single shot if you need to. It definitely seems there is some issues in the implementation of the single shot here. Now I reduced the time base, now it is 50 milliseconds per division, and you can see we were able to capture this power on characteristics of the switching power supply in the background. Now, the only issue is that I can't seem to be able to consistently trigger on this signal. So for example, if I do it again, let me power off the power supply and turn it back on. Oh, now we are able to trigger it. So let's try triggering it again. And you can see this time it's not triggered. Anyway, there definitely seems to be some issue with the single shot mode as I can't consistently trigger on single shot. I mentioned briefly earlier both the volts and millivolts range support the oscilloscope mode. Of course, in the millivolt range, we have much higher vertical sensitivity here. And here, for example, is a 500 millivolts peak-to-peak signal at 1 MHz, and we're measuring it using the millivolts range. And if I switch to volt range, you can see that the signal is very tiny, as the vertical resolution is not there. So here is the same signal in the millivolt range. And let's take a look at what is the highest sensitivity here. So for volts, we can do, looks like we can go down to 50 millivolts per division. That's the highest sensitivity, which is not bad for a portable scope like this one. And let me get to the volt range and let's double check on that. So let's see what is the highest resolution we have. So it looks like in the volt range, the highest sensitivity is at 500 millivolts per division versus the 50 millivolts per division in the millivolt range. And just for completeness, here is a square wave signal coming in at 1 MHz. And you can see because we don't have the appropriate probes, therefore we can't compensate the probe, and you can see the overshot and undershot on the measured waveforms here. And of course you can see, as we mentioned earlier, the update rate of the scope is not that great either. Now let's take a look at the function generator capability. Again, we don't have a dedicated BNC output for the signal. The milliamp socket is multiplexed for signal generator output. Again, this shouldn't be much of an issue as the maximum frequency this meter can output is only at 100 kHz for sine wave, 20 kHz for square wave, and 50 kHz for triangular wave. So as you can see here, now the probes are plugged into the common and the milliamp range. And you can see we already get a voltage output. Now the function generator is only enabled in the voltage measurement mode. So if I change to any other mode, the output disappears. So let's go back to the voltage measurement mode. And let's actually bring up the menu here. So to do that, I just long press this button here. And you can see right now we're outputting a square wave signal at 1 kHz at 3 volts peak to peak. And that's indeed what we measure here on the O1. So let's change our waveform to, say, a sine wave. And let's see if we can change the frequency here. As you can see, we only have these discrete frequency to select from. We can't adjust them continuously. So let's do 100 kHz. And let's see. Yep, that is 100 kHz. And let's reacquire the signal here. It looks pretty good. Also, we can adjust the amplitude of the signal here. So let's do volt. Again, you only have this few discrete levels to select from. So let's do 1 volt peak to peak. No problem. And let's take a look at the other waveforms. Let's do the ramp signal. And you can see this is really a very basic function generator. Alright, time for us to open it up and take a look inside. It looks like there's another screw underneath the QC Pass sticker. We have to take that out as well. Okay, so it looks like there is just a single battery here. Let me actually unplug the battery. I think I may be able to use a clamp meter to measure the current here. So let me actually rearrange a little bit. Let's plug it back in here. Alright, now I get the clamp meter on. By the way, this is the CM2100 from O1, and I did a review of this meter recently, and it's quite nice. So let me zero it out. And let's turn it on. It appears we're drawing about 100 milliamps. Now, can I adjust the backlight? Okay, so this is the brightest mode is 155 milliamps. Let's turn to the dimmest one. Yep, that's 75 milliamps. So apparently that's what the spec was referring to. In multimeter mode, it's roughly 80 milliamps. So let's change it to scope mode. And currently we're drawing 170 milliamps. And let's change the brightness again. So on the brightest level, we're drawing about 250 milliamps. So the backlight actually consumes quite a bit of energy. So if you want the battery to last longer, probably you want to keep it in the dimmest mode. So with our measured current consumption, with a single cell, you can definitely use it for at least a day, especially if you're in multimeter mode. So it definitely seems the battery runtime of this multimeter is adequate. Alright, I just removed the circuit board from the base. It was actually just screwed by in a few screws, so it was fairly easy to remove. I also desoldered the shielding can over the input channel so that we can take a better look. I didn't realize that this hole was actually for the screw. I thought it was for some adjustable component underneath. But anyway, so now the shielding can is removed, and let's take a look. And here is our front cover. You can see there's not much going on there. There is our diode switch and the metal wipers. And before I put away the front cover, let's just take another look. And there's not much going on, except we have these light guides on either side and also in the center here. So that's how the light gets through. And by the way, nothing is on the reverse side as far as components are concerned. You can see we have this LCD here, but not much else is going on here. Now, if you look carefully, you can probably see some of these cutouts. One is here, and one is here. And these are for the LED to shine through. Now, they could have mounted the LEDs on this side of the board, but that increases the assembly cost, as you can't just place the components on both sides without having to glue them on the underside. So this design simplifies the reflow process. And by the way, all the teardown pictures will be uploaded to my website, so you can take a closer look when you get a chance. With the macro lens on, let's take a look at the multimeter section first. You'll notice that, like most of the cheap multimeters we have reviewed, there isn't too much protection going on at the input. We have a PDC up here and another PDC down here, and that's about it. We don't have any MOVs on this board to suppress transients. Now, to be fair, the meter itself is appropriately rated and is only for Cat 2, not Cat 3. Up here you can see we have a couple of fuses surface mounted for lower current range and the 10 amp range. And down here we have a current shunt that is for the 10 amp range. And the digital multimeter section is up here. And this chip here, that's our multimeter chip. Unfortunately, there is no marking on it, which is interesting, as now I'm thinking about it, as this happens to most of the multimeter chips I have seen recently in my teardowns. I'm not sure why it is such a secret. Anyway, here is the EEPROM for the multimeter, and the chip next to the battery connector, that is a TC4056A, which is a lithium-ion battery charger chip. Now, there is an unpopulated footprint right here. Presumably, that is for a different charger chip. Let me move it up a little. If you look at the silk screen, you will see something interesting. Here we have the ET201B and also E1 underneath. So the board was probably made for E1 ET201B model. So clearly it is used for multiple brands, including the MUSTOOL MDS9208 we have here. Now let's take a look at the oscilloscope input section here. The input design is rather interesting, as the signal has to go to both the digital multimeter and the oscilloscope sections. You can see we have 5 of these 2 megohm resistors in series to form the 10 megohm input resistance value. And the reason these resistors are put in series is to increase the withstand voltage. And then another route goes into the oscilloscope channel. You can see the frequency compensation resistors and capacitors in this section here. There are also a couple of relays here to do the physical switching, and there's not a whole lot going on here since this is only a 12 MHz scope. The front end doesn't need anything fancy. Now moving on to the oscilloscope section. By the look of it, all the processing is handled by this STM32F400 ARM processor. The ADC used here is this MDS9208, which is a 10-bit 50 megasamples per second ADC. So the vertical resolution is actually quite good. This is actually the same ADC used in the ZT702S I reviewed a while ago. But the ZT702S used a STM32F403 instead of the 400 used here, and that processor is a lot more powerful than what we have here. So definitely the processing power is the weakest point in this multimeter oscilloscope combo. And towards the middle, we have a header that is for programming the main processor, as on the reverse side you can see the traces actually go to that processor here. And that's pretty much everything on this board. Overall, the MDS9208 is quite decent. I really like the multimeter implementation, especially given that it is the primary functionality of this meter. Now, The oscilloscope implementation definitely has some bugs, especially in single-shot mode, although I don't know if people using this meter would actually use it for single shot at all. The overall manual design is actually very well thought out and intuitive, and it allows you to get to most of the settings with just a few button pushes, considering it only has 7 buttons. Let me know what you think about this meter in the comment section below. Anyway, I hope you enjoyed the video. If you liked the video, please don't forget to give it a big thumbs up, and remember to subscribe to the channel for more videos like this in the future. I will catch up next time.